Alrighty, welcome to the Chapter 3 physics video. This one's going to be about motion again, similar to Chapters 1 and 2, but now instead of having everything move at constant speed, we're going to allow things to accelerate and see how that affects the position and velocity. One important thing is we're only going to be doing this in one dimension, so things are only going to be moving forward and backward along a straight line path. So a good example of this is when you drop things and they fall in a vertical straight line, or if maybe cars are driving forward and backward on a highway, it's all in a single linear motion, but nothing is veering off side to side. Later on we'll worry about 2 dimensions and then 3 dimensions, but for now everything is just moving forward or backward. So first we'll talk about what acceleration is, then negative acceleration, how to graph this kind of stuff, how to think about these graphs in comparison to the position and velocity graphs we learned about earlier, and then we'll look at some problems involving constant acceleration, the formulas that you're going to end up deriving because the acceleration is constant. You can then work backwards mathematically and find out about position and velocity. A special case of accelerated motion, which is freefall, and then finally some problem-solving strategies and example problems. So let's start off just what is acceleration. It's a word that we use all the time in our regular English vocabulary, and for the most part our use of it is accurate in terms of the scientific meaning. So acceleration is a change in velocity over time. That's the scientific definition. So when you talk about your car accelerating, it's increasing its speed, and therefore it's increasing its velocity, so it is accelerating in a physics sense as well as in a normal English sense. Our formula for acceleration is delta v divided by t. Delta v is the change in velocity, and of course divide by time. So if you have a large change in velocity in a very small amount of time, your acceleration is very high. If it's a very gradual speed up, it takes a lot of time, so the more time it takes here in the denominator, the more time it takes, then the slower your acceleration is going to be. Okay, so these are just 2 fun pictures to illustrate. When we think of something accelerating or moving very fast, it's going to be a blur if you have a time-extended photograph. Our symbol for acceleration is going to be a, and our units are meters per second squared. The reason it's meters per second squared is because the velocity here, the velocity is already meters per second, and then you're dividing that by seconds. And if you think of your math skills, if you divide by seconds and then you divide by seconds again, you get meters over seconds squared. So lots of fractions in fractions in this section. Alright, so acceleration is the change in velocity. So what is a negative acceleration? The key to remembering this is that it's not slowing down because acceleration is a vector, which means direction matters. So negative acceleration, that just means your velocity is getting more negative, but that doesn't actually mean you're slowing down. So there's a lot of different scenarios because it depends which way you're actually traveling. So if we think about a compass and we define north as positive and we define south as negative, then you can start to kind of think about what would be a negative acceleration. Any acceleration in the southward direction would be considered a negative acceleration. So if you're moving this way, if you're moving upward in the north direction, and you have an acceleration in the southward direction, what's that going to do to you? It's going to slow you down. Okay, but that in this case is a negative acceleration because the acceleration is in the negative direction, south. So in this case, it's slowing you down and it's a negative acceleration. But imagine you were already traveling in the southward direction, and then you had a negative acceleration, which means you're accelerating in the south direction. That means you're accelerating the same way you're already going, which will actually speed you up. So whether you speed up or slow down depends on whether or not your acceleration is pointing the same direction as your velocity. So let me say that again. If your acceleration is pointing the same direction as your velocity, that means you're accelerating in the same direction you're moving, which will speed you up. If your acceleration points opposite direction of your velocity, whether it's north-south or south-north, as long as they're opposite, you'll be slowing down. So in your head, when you see negative acceleration, you almost always automatically think, oh, it's slowing down. But just be very careful that it's not always going to mean that. So let's look at 3 examples. If your velocity goes from 10 to 7, then you had a negative acceleration because your velocity changed. The delta v here, delta v, is final minus initial, so 7 minus 10, which is negative 3. So you have a negative change in velocity, you have a negative acceleration. If your velocity goes from negative 5 down to negative 15, here you're speeding up, right? You're actually going faster. 15 meters per second is faster than 5, but because it's more negative, it is a negative acceleration, but speeding up. This was a negative acceleration, but slowing down. And then how about here? Your velocity goes from 2 to negative 2. Here, your velocity goes from positive 2 to negative 2, so you're getting more negative. So all three of these are negative acceleration. In this one, you're slowing down. In this one, you're speeding up. In this one, think about what's going to happen here. You're going to go from 2 to 0, which means you were slowing down, and then from 0 to -2, which means you were speeding up. So you ended up at the same speed as you started, but you slowed down and then you sped up in the opposite direction. So in this case, positive velocity, you might have been going north, you slow down, stop, turn around, and then at the end you're going south, opposite direction, in the negative direction. So negative acceleration just means your velocity is getting more negative. It doesn't mean that you're always slowing down. I was going to do some examples here, but I just did them kind of right here, so I think this is good enough. All right, let's look at some graphs. I know that these graphs are pretty abstract. We talked about these for position. We also talked about these for velocity. So we're going to use the same set of 6 graphs and reinterpret again what the meaning of these graphs is if you think about the y-axis now as acceleration. So if we think about this as acceleration for all 3, let's talk about the motion. What's the object going to be doing? And in all cases, let's assume that the object starts at rest. Okay, so this one, it's accelerating at, say, 30 meters per second squared. So if it starts from rest, it's taking off from rest and it's going faster and faster and faster. So this might be a drag racer at the start of a drag race, and it takes off and it's accelerating. It's increasing its velocity. Okay, this one is also going to be accelerating, but at a much lower rate. So this might be an old lady in her car taking off from a stop sign, right? She's going to be increasing in speed, but at a slower rate than the drag racer over here. Okay, how about this one? This one, the acceleration itself is increasing. So you start off accelerating, but not very much, and then over time you accelerate more and more and more and more. There are very few things in the world that can actually achieve an acceleration that looks like this, where in the beginning you don't accelerate that much, but the faster you go, the more you accelerate. In most cases, the faster you go, the less you can accelerate, because you're already going really fast. It's hard to go even faster. Imagine in your car, when you try to accelerate from 0 to 10, it's pretty easy, but to go from like 60 to 70 is not nearly as easy. So this graph, what it's saying is your acceleration is getting faster, or higher and higher acceleration, but again, it's not very realistic real world. This one's the same thing. Your acceleration is increasing over time, but here instead of starting with 0 acceleration, you started with 2 meters per second. Okay, this one is a lot more realistic. You start off with a very high acceleration, but over time you decrease your acceleration, and when you get to here, you're not accelerating at all. Does that mean you're not moving? Absolutely not. You are moving, but you're going to be moving at constant speed. So anytime your acceleration is 0, that means your velocity is constant. You're not speeding up or slowing down. So anytime an acceleration graph crosses the axis here, the x-axis, that means you're moving at constant speed. So here, you started off moving at constant speed, or actually at rest. Then you accelerate faster and faster, and then you accelerate less and less and less, and you end up going at constant speed. But again, you are actually moving. By the time you get to the end of this graph, after 10 seconds, you're moving pretty fast. Because during this part here, right, if we imagine our velocity, let's do this one. If you imagine the velocity, you're accelerating, right? So your velocity is going to go up. And here, you're still accelerating, but not quite as much, so your velocity is going to go up some more. And then here, you're moving at constant speed, so now your velocity is going to be stable. And the curvature of this graph will actually be kind of like this. It'll curve up like this, and then it will curve like that. Because this right here is your highest acceleration, so it's your steepest change in velocity. Here it's a very low acceleration, so it's a very gradual increase in velocity. Here it's a very low acceleration, so it's a very gradual increase in velocity. So this curved line here really is the actual shape. I just drew the straight line to show that it's increasing. Okay, so we can relate the 3 graphs together from position to velocity to acceleration. I need a blank slide for this. Let me add in a blank slide. So how do we relate the 3 graphs together? We're going to look at how you can go from a position graph to a velocity graph to an acceleration graph, and then back the other way again by looking at the slope of the line and the area under the curves. So let's take, for example, a position graph. So if you have x and t, and say your position, you start off here, and then you come down here, and then you come here, and then you come here, and then here, and then back. Something like that. So let's make these increments. And say you want to find your velocity against time. So right here, your position is staying the same. So that means for this first segment, your velocity is actually 0. Okay, then here, you're moving from some positive value down to the origin. So you're moving in the negative direction. So for this segment, the second segment, your velocity is going to have some negative value. Then here you're at rest at the origin, so your velocity is going to be 0 again. Then here you're moving in the negative direction again, so you're going to have a negative velocity again. Then from here to here you're at rest at some negative value. And then from here to here you're moving in the positive direction, so you have some positive velocity. So this is not 100% realistic because you can't go from having a 0 velocity instantaneously to have some negative velocity. So there's going to be some gradual, like little steep curved line here. So this will have to be a rounded corner in real life, but we're going to model it by just allowing there to be these kind of instantaneous changes in velocity. Go from this to this to this, like different segments. So let's see if this makes sense. Anytime that this position here is horizontal, you have 0 velocity, 0, 0, and 0. So the slope of this line is 0, 0, 0. So the slope here is your velocity. So your slope, and the reason is because mathematically, slope is delta y over delta x, and our y-axis here is position. So that's delta, let's call x for position, over t, and your definition of velocity is change in position over time. So here this x is position, and just keep that straight from this x, which is the x-axis. I apologize that it's the same variable twice, but mathematically we use x for the x-axis, and mathematically or physics-wise we use x for position frequently. So your velocity, you can see, is the slope. Now if we want to go from velocity to acceleration, let's look at this. Okay, acceleration, recall, is a change in velocity over time. Okay, so where is the velocity changing? Here it's stationary. Here it's changing from 0 to some negative value. So the acceleration is 0. And then at this one little moment in time, that very, very short duration in time, we get an acceleration. And then we're back to 0 acceleration because the velocity is constant again. Okay? And then from here to here, though, here our velocity was negative, and now the velocity is 0. So that's a positive spike. We went from a negative value up to a positive. Positive. Now we're at 0 again here. Then right here we went from 0 to a negative velocity, so a negative spike. Then we were at 0 again, 0 again. Here we went from negative to positive, and then we were at 0. Here we went from 0 to positive, so a positive spike, and then 0 here, and then a negative spike. So you can see the correlation here. I'm going to try to line these up. You can see the correlation here. Anytime your velocity changes towards a more positive value, you have a positive spike on your acceleration. That means you kind of got pushed or kicked in that direction. So let's see if it makes sense. If you're at rest and you want to be going in the negative direction, you need to kick in the negative direction. So maybe you get kicked in the negative direction. Now if you're already moving in the negative direction and you want to come to a stop, you have to get kicked in the opposite way that you're going to slow you down and stop you. So this is a positive kick to slow you from this negative velocity back up to 0. And then the trend continues. So once again, you're looking at the slope here. So the slope of this line is negative, the slope of this line is positive, negative, positive, positive, and negative. And if this slope was perfectly vertical, if it was a perfect instantaneous change from 0 up to positive, then the slope of this line would be undefined or infinite, and this spike would kind of be an infinite spike, which is obviously not the case because there's some small duration of time. So this line is very steep, but not infinitely steep or not undefined slope. So this spike right here will be very short and very tall, and that will cause the change in velocity. Okay, alternatively, we could think about starting with the velocity and figuring out the position or the acceleration, or starting with the acceleration and working backwards to figure out the velocity and the position. So I'm not going to start you with an acceleration graph typically because these spikes are very hard to interpret in terms of, okay, well, how much is the velocity changing? Like, if the spike is negative, you know that means the velocity is getting more negative, but it's hard to figure out exactly how much. So this is more of a qualitative idea, whereas here, to go from velocity back to position, we can actually measure it and calculate it. So, because here, whatever this known velocity is, say this is like -3 meters per second, and whatever this duration is time, and say this is t equals 1 and this is t equals 2. So from here to here is 1 second, and our value of our velocity was -3 meters per second. You can figure out how far you've actually traveled during that time, right? So if you're traveling 3 meters per second in the negative direction for 1 second, you've traveled a total distance of 3 meters. So the distance traveled during this interval here has to be 3 meters. So if you went from here to here, this must have been 3 meters, and this must have been 0 meters, right? So you can work backwards by looking at the velocity and the time. And so what this turns out to be is if these are rectangles, or even if they're not, the area here, the area is x times y, which is velocity times time, which is distance. So the distance, I know this is getting messy, I apologize, let me change colors. The distance here is the area under the curve. Okay, so just to reiterate, to go from position to velocity, you're looking at the slope of the line. To go from velocity to acceleration, you're looking at the slope of the line. To go backwards from velocity to position, you're looking at the area under the curve. And if you've taken or are planning to take calculus anytime in the coming year, or you're taking it right now, or you took it last year, you'll see that these are derivatives and integrals. So they're very, very closely related to calculus. And anytime things are fluctuating or changing, you can find rates of change or areas under curve using calculus. So there's a very close connection. All right, so we've moved on from the graphs. Now let's think about some formulas that will explain the motion. So the graphs are really, really good to kind of visualize what's happening, but they're not going to very easily give you exact values and allow you to solve problems. So this set of 5 formulas, 1, 2, 3, 4, and 5, is really going to be what you use to do almost all the problems in this chapter. So let's think about these formulas in terms of the graph and see if we can make sense of them. So if an object is accelerating at a constant rate, okay, or if we know the average value, typically it'll be constant, or if you know the average value, then the average value will be constant, we can figure out the velocity and the position, the time, the acceleration, the distance, any of those kind of variables. So once you know acceleration is constant, the final velocity is going to equal the initial velocity plus the acceleration times time. All this is a rearrangement of your definition of acceleration. So if you recall, the acceleration definition was delta v over t. So delta v is v final minus v initial. And if you rearrange this, multiply both sides by t, and then subtract, or rather add vi to both sides, you can very easily get this one. So this one you should memorize immediately. Or if you already have this one memorized, then you already know this one kind of by default. Okay. Here's an equation to find your final position. So if you know your initial position, you know your initial velocity and how long you were moving, and you know your acceleration and your time, you can find your final position. So with any of these formulas, it doesn't matter which variables you're trying to find. Like this formula here, it's written in a way that allows you to find x final. But if you know, say, x final and x initial and t and a, you could find v initial. So as long as you know all the things except one, you can find out that one unknown. It's just important that you know all but one. If you have 2 unknowns, then you'll have to use 2 equations. If you have 3 unknowns, you'll have to use 3 equations. So you're going to do a lot of system of equations, 2 equations, 2 unknowns, things like that you've learned about in Algebra 1 and Algebra 2. This next equation here is a combination of equations 2 and 3, which is solved by eliminating time. So v final squared equals v initial squared plus 2ad. D here is the displacement. In all these equations, we're again assuming linear motion, so you're just moving in a straight line, and d is the displacement. V average, finally, is v final plus v initial over 2. That's just the definition of any average, but it's also the total distance over time. So there's 5 variables that you have in any of these equations. You've got the acceleration, you've got the distance, you've got the time, you've got the initial velocity, and you've got the final velocity. Because if you're accelerating, obviously you have a different initial velocity than final velocity. It takes you some time to do that, to increase your speed from v initial to v final, or decrease. And lastly, you're going to be moving or traveling some distance while that happens. So there are these 5 variables in all the problems, and your task is always going to be to figure one of them out. Sometimes you'll be given 4 of the other ones, sometimes you'll only be given 3 of the other ones, but you have to be given at least 3 to find the other 2. So because of these different equations and relationships that we have, as long as you're given at least 3 variables, you can figure out the other 2. Sometimes, you'll be given any combination and you can be asked to find any of the other ones. So this is a real math puzzle in terms of selecting which equation you want to use to find the unknowns, and we'll talk about some strategies to do that in a moment. Okay, first I want to prove this formula to you using geometry. So if we have a graph and we start at some initial velocity and we end at some final velocity, and we accelerate uniformly from the initial velocity to the final velocity, and that takes us some duration of time t, and we started at 0. We can break this shape into a rectangle. So we already said that the area under the curve will give us the distance, right? So the area of this rectangle right here is the length, which is the time, times the height, which is the initial. So the rectangle area is v initial times t. Okay, this triangle here, it has a base of t and a height of v final minus v initial. But you can see from this equation right here, if you subtract v initial from both sides, you can get that v final minus v initial equals at. So the height on this side is also equal to at. Okay, so this triangle here has an area of 1/2 base times height. The base is t, and the height is at, for a grand total of 1/2 at squared. So this formula here to find the final position, your ending position is equal to your starting position if there's no velocity or acceleration. So if you cover up all this stuff, you just have final position equals initial position. So that makes sense. But if you're moving, then you have to add on the initial position times time. Okay, the initial position times time comes from this triangle, or sorry, from this rectangle, and then the 1/2 at squared comes from this triangle on top. So the reason is because as time goes on, you're moving faster and faster and faster and faster. So you're accumulating more and more distance traveled, and it's not linear, it's proportional to the square of time. So if time doubles, you more than just double your distance because you're not moving at a constant speed, you're moving at a faster and faster speed. So you don't have to memorize the derivation or the proof here geometrically, but you definitely have to memorize all these formulas, and not just memorize, but understand and know how to use and manipulate these equations. Okay, we're almost finished. We just have to talk about freefall and then some practice problems. So in the world, there are a lot of ways that you could experience constant acceleration, but none of them are as common as freefall. So freefall is the definition of an object falling through Earth's atmosphere, or just experiencing only gravitational forces. So in order to be in freefall, in a physics context, you need to ignore air resistance, okay? I know in real life, any of these situations where someone is skydiving or jumping, bungee jumping, etc., you're going to have to take air resistance into consideration. But for this class, we are defining freefall. So if something is in freefall, then only force of gravity is on it. And if only the force of gravity is on something, then its acceleration is caused exclusively by gravity. And there's a known measured value for the acceleration caused just by gravity, and that is 9.8 meters per second squared. So we'll talk about this in the next chapter, about how this value came to be and how it's related to the forces acting on different objects. But for now, for just looking at the motion of things, we're not going to worry yet about the forces that cause that motion. You just need to use, instead of using a, we'll put in a lowercase g, and that will represent 9.8 meters per second squared. So I want you to write the lowercase g instead of 9.8 meters per second squared all over on your paper, because it's just faster to write little g, and you're going to be using it a ton all this first semester and even into second semester. So just get used to writing little g all over the place. Little g, little g, little g. And anytime you see the little g, in your head you're thinking, okay, 9.8 meters per second squared. The value can be positive or negative depending on your coordinate system. Typically, you're going to have down as negative and up as positive, and therefore you'll plug in a negative 9.8 for the acceleration. But again, it depends on your coordinate system. You could define down as positive if you wanted to. Okay, let's look at some problem-solving strategies and then apply those to a couple of practice problems. So the first thing that you should do when you're attempting a new problem is draw a simple diagram to illustrate. I don't mean a full-out sketch with everything, perfectly drawn to scale, just something very simple so you can kind of imagine what's going on. And it also allows you to simply label the different things that you know, like the initial velocity or the final velocity or how far it traveled. Okay, once you have everything written down and labeled, then you want to select the correct equation or equations and write them down. I can't emphasize enough how important it is to write down the equation in terms of variables before you plug in your numbers. So if you're going to be using the formula VF equals VI plus AT, you should actually write down VF equals VI plus AT before you start plugging in all of your numbers. And there's two reasons for doing that. The first reason is that it helps ensure you plug the right things into the right place. If you're not actually looking at the equation, if it's just in your head, it's easy to get things mixed up or change a plus sign to a minus sign, etc. And the second reason it's so important to write down the equation first is that I want you to practice solving equations symbolically and not numerically. So what I mean by that is if you were to try to solve this equation for A, instead of plugging in number here, number here, number here, and then rearranging it mathematically with numbers all over the place, you can rearrange this equation just using variables and symbols like minus vi, divide by t, whatever you do to one side, you have to do to the other side. And at the end, you'll have an equation, A equals Vf minus Vi over t, which we kind of already knew because that's the definition of acceleration. But the point is, you're symbolically manipulating it to get from one equation into another. And once you have the equation solved for the variable that you're interested in, that's when you'll plug in your numbers. The reason for doing this is, it's actually easier to rearrange in terms of variables than with numbers, and you have a much less chance of making a mistake. I know at some point students are often more comfortable rearranging equations with numbers everywhere, but I promise you that you'll see some long-term benefits if you practice and you start transitioning into rearranging symbolically. It's much more time efficient, and you have a decreased chance of making a mistake. So once you plug in your numbers and you get your final answer, always remember to check your units, make sure that what you've plugged in is in the correct units and what comes out is in the units that you expect it should be and that the value is reasonable. Alright, let's make a couple practice problems. How high is a window ledge if a vase is gently knocked off horizontally and hits the ground 1.2 seconds later? So this is what I mean by a quick sketch. Here's a window ledge, here's the ground, here's the vase, it gets knocked off, and I can say time equals 1.2 seconds. Okay, what else do I know? It's gently knocked off horizontally. So what's its starting velocity downward? Velocity initial is going to be 0. Velocity final when it hits the ground, we don't know that. The acceleration, well, if this object, what's causing it to fall? It's in free fall because the only force on it is gravity pulling it down. So therefore we know the acceleration is negative 9.8 meters per second squared, and I'll choose my coordinate system to be positive as up and negative as down. Okay, and I'll have it end at height equals 0 and start at height equals unknown. So the distance that this thing is going to fall is a distance of h minus 0, but it's ending at a lower place than it started at, so our distance is going to be negative h. The distance traveled is from h down to 0, so therefore negative h. So now when I look at all of these things that I know, I can ask myself, okay, what equation can I use that has a good relationship between time, initial velocity, acceleration, and distance? Now, notice I don't know the final velocity. So let me go back to the formula switch. You should have written down maybe on a note card or something that's handy that you can have with you when you're solving problems in your homework. I don't know the final velocity, okay? So I don't want to pick a formula that has final velocity in it. So this one here is not going to be useful. This one here, it doesn't have final velocity in it, so that seems like a useful one. This one has v final, this one has v final. So they all have v final except for this one. So anytime you have something and you don't know the final velocity, this is likely a good place to start. Okay, so let me get back to here. So I want to write it down. Position final equals position initial plus VIT plus 1/2 AT squared. Now there is one modification that you can make to this formula, which is the final position and the initial position. If you subtract the initial position from both sides, minus x initial, the final position minus the initial position is just the distance traveled. So in most cases when I'm using this equation, I don't write x final and x initial. I just put distance equals VIT plus 1/2 AT squared. Okay, what is it that I'm trying to find? I'm trying to find how high the window is, which is the distance. So I can now plug in my numbers because I don't need to rearrange anything because it's already solved for the variable that I want. So plug in VI and t. Well, VI is 0. Okay, 0 is gone. Plus 1/2. Acceleration is negative 9.8. And time is 1.2 squared. Notice I didn't write meters per second squared and seconds right here because I know that if I plug in meters and seconds, which are appropriate SI units, then I'm going to get out the appropriate SI units. Okay, so now I pull out my calculator and we type it in 0.5 times 9.8 times 1.2 times 1.2. I get 7.06. 7.06 meters for distance. And even though this came out to be negative, I know that my distance is supposed to be negative h, so my height is positive here. And so what I want to say about solving problems and using positive and negative values for acceleration and distances and heights and stuff like that is use the equations to get your numbers out and use common sense and logic in your picture to determine whether it's positive or negative, whether it's position or velocity or acceleration. Use your common sense and your logic and your understanding of these physics principles to determine the sign, and use the equations to get the magnitude or numerical value. So clearly the height of this is positive 7.06, not negative, even though the distance was negative. So the distance is negative because it moved downward, but my final answer is how high is the window, so the height is positive 7.06. Okay, next one. How fast is a race car going at the end of a 400-meter straightaway if it accelerates at 4 meters per second over the full distance and hits the straightaway already going 40 meters per second? So let's draw a little racetrack here. So the straightaway is going to start here and end here. So it's going to have a V initial right here. It's going to have a V final right here. It's going to have some distance that it's traveling. And it's going to have some time value and acceleration value. So it's going here to here. So let's write down what we know. V initial, at the point it hits the straightaway, it's already going 40 meters per second, so we write that down. V final, how fast is the race car going at the end? So that's what we're trying to find. Put a star by it so we know that's what we're looking for. How about the distance? How far is it traveling on this straightaway? It's a 400-meter straightaway. How much time does it take? It doesn't tell us how much time it takes, and we're not trying to find it, so we maybe don't need that. Do we know the acceleration? Yes, the acceleration of the car. It accelerates at 4 meters per second squared for the full distance, so the entire time it's always accelerating at 4 meters per second squared. Notice I always put my units on these starting numbers. That way, if anything is not in the standard units, I can immediately convert the units to the number that I want and change it and make sure that what I'm plugging in is going to be the good, appropriate units. So we need to find a relationship between V initial, V final, distance, and acceleration. And it does not need to include time at all. So if you go back and look at your formula sheet, go through that list and try to see which one has the relationship that you want. And it turns out it's this one. V final squared equals V initial squared plus 2AD. Okay, we're trying to find the speed of the race car at the end, so we should solve this by taking the square root of both sides, and then we have that V final equals the square root of this stuff. So now we can plug in our numbers. V initial squared is 40 squared plus 2 times acceleration is 4 times distance is 400. Okay, we know the car is speeding up because its acceleration is positive in the same direction that it's going. So this is positive acceleration and positive velocity. If the car would have been slowing down, we would have needed to put in a negative acceleration to show that it's the opposite direction that it's moving. In any event, we can now type this into our calculator. And using common sense, we know the answer has to be more than 40 because the car is speeding up. So let's see what the final velocity is. 40 squared plus 8 times 400, okay, and then take the square root. I get 69.3 meters per second as the final velocity. Alright, so if you type this in your calculator, which I encourage you to do, you should get the same answer. And does it make sense? Yeah, it seems pretty reasonable. The car's traveling at 40 meters per second for 400 meters, so that would take around 10 seconds, but it's going to take less than 10 seconds because the car's speeding up as it goes. So if it took the full 10 seconds at an acceleration of 4 meters per second squared, it would have increased by 40 meters per second up to a final speed of 80. But because it was speeding up as it went, it's going to be less than 80, and again, 69.3 is less than 80. So the answer seems reasonable given all this other information and constraints that we have. All right. Last problem. What was the average speed of the race car on the straightaway in the previous question? Okay, well, we know the final velocity is 69.3. We know the 0.3 meters per second. We know the initial velocity was 40 meters per second. So V average should be pretty easy to get by just doing VI plus VF over 2. But notice it's also distance total over time. So whichever one of these looks easier is the one we should use. Well, since we know VF and VI, it's much easier to do this one. So if I do this one, let's call 69.3 around 70. The average of 70 and 40 is going to be around 55 meters per second. It's a rough estimate. Okay? If we knew the distance and the time, we do know the distance, that was 400 meters, but we don't know the time, so this one's not as convenient to use. Now certainly we could calculate the time. And then plug it in and show that we get the same answer, but that's something you can do if you want to, but I don't think it's necessary at this juncture in time. Alright, so just to recap, you've got accelerated motion, which means you're changing speed. You could be speeding up or slowing down. Anytime something is experiencing uniform acceleration, which means it's accelerating at a constant value, or you know the average acceleration over a period of time, you can use that block of equations. You should probably write those down on a note card or something and have it with you all the time. You're going to need them memorized for the quiz, whenever the quiz is, next week or tomorrow or whatever day it happens to be. And when you're doing your problems, make sure you draw a little sketch. Write down all 5 variables so that you know what you have and what you're looking for. Select the equation or equations that seems appropriate. Notice that on the harder problems, you might first have to solve, say, one equation and get a sub-intermediate answer, and then use that intermediate answer in a second equation to get the final answer. So there are some harder examples that will require you to use 2 equations to get what you're looking for. And I encourage you to struggle through these. I think there's a lot of homework and some of the problems are difficult, but the very best way to learn this stuff is to bump your head up against them, get stuck, try it again, try a couple different ways, get help from me or look at the solutions online on the website, and then eventually it'll make sense and you'll have a lot better understanding than if someone just holds your hand all the way through, because then you'll get the answers right the first time, but you won't really understand why it's working. So good luck with the homework, and let me know if you have any questions in class.